Okay, this video is about area between two curves. Area between two curves. And the idea that you're familiar with is the area under the curve. So that would be this thing here. So in Calculus 1 we talk about approximating the area under the curve using an infinite number of rectangles. So this is the basic idea you can see in the picture. So if we wanted to call this function f, then we could actually get the exact area under the curve. So this shaded area here, right, we would integrate, right, the function f of x dx, and we go from a to b, right, lower bound to upper bound. So that's the basic idea. And in the picture here we could see this would be from 0 to 4, right? So what we see in the picture is an approximation. This thing here, right, is going to give us the exact area underneath the curve. So I'm going to just shrink this here, kind of move it out of the way here. And so what we do here is we extend this idea to the area between two curves. So it's a little bit different, but it uses a lot of the information that we already know. And so this is how it works. So I draw a little picture. So we could have a function here, we can call it f, and maybe another function here, we could call it g. And instead of talking about the area under the curve, we're interested in the area between the two curves. So I'm going to draw a little line here. I'll call this A, little line here, and call this B. And so the area of interest would be this little portion here. So you can see right away this is going to most certainly use this content over here, right? The idea of the area underneath the curve. So the quick way of doing this is we can find the area underneath the f function, right, under f, and that's going to go all the way to the x-axis, and then we can subtract off the area under g, right, and that's going to leave us with the shaded area, this little portion here that we see. So I'll just write this out, right? So the area, and when we talk about it, we're really talking about this little piece, right, so this area. So the way that we're going to set this up is we integrate from a to b, f of x dx, right? So that's also going to give us this little portion of area here, right? Because that's going to include the area underneath f, but above the x-axis. So we have to remove a portion here, right? We have to subtract area from a to b, g of x dx. So this little thing here is going to be the area bounded by the two curves, or the area between the two curves. And because the integration is with respect to x, we typically combine the f and the g into one integrand, so we can express it that way. So this is the way we'll usually see it written here. I'll write it down right here. So bounded area. So we would go from a to b, and so we have f of x minus g of x, and I'll just put these in parentheses, so we really express it as one thing there. So one way, one little device you can use to help you remember this, you could see, I'll just use my cool little pointer here, right? This function f is the top curve, and function g, right, is the bottom curve. And if that happens throughout the window of integration from a to b, then one way of remembering this is it's really top curve minus bottom curve. So I'll just emphasize this here. This is one way of remembering this, right? It's really top minus the bottom. So that's just a little device that you can use, right? And that's really all that there is to it for area between two curves. You're more or less just using this idea from Calculus 1 twice to really grasp that. So what we should do is probably look at an example. So I'm just going to get this stuff here out of the way. I don't really need that. And let's go get an example. Alright, so here we are. Find the area bounded by the two parabolas, y equals x squared, and then this other parabola here. So y equals 2x minus x squared. So naturally here, sketching a picture is important, right, to have an idea of what curve is on the top and what curve is on the bottom. And then you set up the integral and just evaluate it, right? And that's really all there is to it, to these types of problems. So I'm going to shrink this, and then let's just do it here. So given these two curves, I'll highlight this here. So we have this one and this one. What you may want to do to find your A and your B is to find the points of intersection. So it's not something you really have to do. It really depends on the problem. But I'll go ahead and do it for this one. So we have y equals x squared and y equals 2x minus x squared. So this one is set up where the y's are equal, so you could just set these two equations equal and find the points of intersection. So I'll just take a minute to do that. It should be pretty quick. So I'm going to subtract x squared from both sides. And yes, this is a rolling. I remove a 2x, so 1 and then minus x. So you could very quickly get these intersection points. X is 0 and 1, right? So most likely those two values, these two guys here, right, they're going to be your A and your B, right? It really depends a lot on the picture as well, so you can't take those things for granted, but that's often the case, what's going to happen. So I'm going to draw a small little picture here, and then we'll set up the integral. But this problem is, the hard work is almost done. So I'm going to look at these different curves here, right? So this will have 0, 0, and then also 1, 1. Right, so all I'm using there is just the fact that x is 0 and 1. So you want to figure out the y coordinates as well, and then just plot the points. So I don't really know exactly what this is going to look like, but I'm banking on it being pretty small. So we have 0, 0 here, and then also 1, 1. And then I'm very familiar with what this looks like. Right, sort of like that. And then the other curve, you can do the same type of thing with this one. So I'll put a 0 in here, right? So this will be 0, 0. And then the same thing happens here, right? 1, 1, because they should be points of intersection. And this is a parabola opening downward, so I'll put this in a different color. And so this might not be perfect, but be good enough, right? But if you look at this, you could see the area bounded by the two parabolas is this little portion here, right? And so the idea, right, if you want to go back and think about the Calculus 1 concept, right, of using the rectangles, right, this is our little representative rectangle that we're talking about. And you could see the rectangles here are top curve minus bottom curve. So really it's the parabola opening downward, right, that's the top curve, and then the parabola opening upward is the bottom curve. So you set up the integral, and that's it, right, you just do the work. So let's give that a shot here. Let me shrink a couple of things here because we have all the important information. I'll just move this here, and let's just do it here, right? All right. So the area is equal to, right? We're going from 0 to 1, and then top curve minus bottom curve. So 2x minus x squared. So that's top minus the bottom, which is that. And it's always good to put an extra set of parentheses in there. And that's it. I mean, once you can evaluate that, then sometimes we'll even stop in class just doing the problems this way. But I will take this one all the way to the finish line. I should do that once in a while. Alright, so this is what the problem looks like. It's up to you what you want to do at this point. I would remove the 2. Makes the mathematics a little bit simpler. So it looks like this. And then this one is almost done. So the antiderivatives here are pretty simple. It's x cubed over 3. Insert your limits, and the area is pretty much here. Right, so we only have to, in this case, right, insert the upper limit of integration because 0 will knock out that whole result. So this will be 1/2 minus 1/3, right? So that's going to give you, 3 over 6 minus 2 over 6, so it's 1/6. So I'll just finish it here, right? So this is 2 times 1/6. So you're just going to get 1/3 out of this. Right, so remember here, when you're calculating these things, this is area, so the units on here will be something like square meters or square feet. So they are squared units, and that's something always good to look at. And we should probably just go back and interpret this, right? Make sure this is good, right? So if you go back to this picture, my picture isn't perfect, but you could probably see what we need to see here. So if we just look in this little confined area here, so this is a unit square, right? So a 1 by 1 square will have an area of 1, and what we're saying here in the calculation is, let's make sure this is right. So the area is 1/3, and that looks pretty reasonable, right? Glancing at this picture, so we're really saying, using my fancy pointer again, that this little portion here accounts for 1/3 of the area in the square. The other 2/3, right? You'd have 1/3 here and another 1/3 there. So that looks like a pretty reasonable calculation there. All right, so the last thing here, this is one more thing to talk about with area between two curves. This is that top minus bottom isn't always the most convenient way to do things. It really depends on the diagram and what kind of information that you have. So I'll just sketch the picture here, and we'll probably talk more about this in class. So sometimes the picture might be situated differently. So you might have a curve here and say a curve there, something like that. So you can see top minus bottom here is a little bit ambiguous, but we could cut off this diagram here, maybe call this C, and then cut off the diagram here, maybe call this D. So you should stop and think about this for a moment, because now all we're going to do is to integrate along the y-axis instead of the x-axis, right? So the idea here is we're going to integrate from the lower limit C all the way to the upper limit D, right? And the integration is thought of as moving in this direction, right? Otherwise, the idea is very similar. So if you're moving in that direction, then your curves are different, right? This here, we would have x as a function of y, so I could call this f of y, something like that. And then this here, we would have x is a function of y. So you can see the top minus bottom idea is almost the same here. The only difference is we're talking right minus left. So this is our right curve, and this is the left. Right, so if we just think of the rectangle sitting this way, this is a little hard to do, right? So we think of our rectangles this way, and then if you think of the width of this here, this is dy, right? So that little width in the vertical direction is dy, so all of the integration will be with respect to y. Let me see if I can erase some of these spots here. And so that's the idea that we'll explore more of in class, but I'll just write this here, what the area will be. So the bounded area. Right, so we integrate here from C to D, and it will be right curve minus left curve. So according to this diagram, it'll be f of y minus g of y. And then we close this with dy. So something you can think about is there's a lot of problems that you could actually do both ways, right? Top minus bottom and right minus left, but there are definitely advantages to one over the other, right? Just depending on the problem.